Hi everyone, I am Devraj going to demonstrate to you estimation of Fe2 plus by potentiometric method. Estimation of Fe2 plus is an essential for a very simple reason that most of the industrial effluents, domestic effluents contains Fe2 plus. Also our biological fluid contains Fe2 plus. So estimation that gives a lot of information about the wastage as well as our biological fluids. So you must have learned how to estimate Fe2 plus by a titrometric method using an internal indicator diphenylamine, wherein you would have relied upon the color change. Herein the basis for this titration actually from the Nernst equation. So there is a potential change associated with the oxidation of Fe2 plus into Fe3 plus by the potassium dichromate. So we follow that. By following the potential change associated with that redox reaction, we will be able to estimate accurately the amount of Fe2 plus present in the given solution. The equation is here, the chemical reaction, redox reaction is here. Fe2 plus gets oxidized into Fe3 plus with the help of the oxidant's potassium dichromate in acidic medium, right. If you write a Nernst equation for this, the potential of the reaction is equal to standard electrode potential plus RT by NF, where R is a gas constant, T is the temperature at which you do the reaction, N is the number of electrons involved, which is 1, F is a Faraday, ln product by reactant. Here you see three different products, Fe3 plus, so reactant, corresponding reactant is Fe3 plus, the power source their corresponding concentration term, and then chromium 3 plus divided by chromium 6 plus, which is the reactant, and the activity factor for the product water is 1 and divided by the concentration of H plus. Since we are estimating only Fe2 plus, we are taking consideration of only the oxidized and the conventional Fe2 plus concentrations. So the equation simply turns out into E is equal to E naught plus, after plugging in all the parameters for RT by NF, 0.0592 log of Fe3 plus by Fe2 plus, right. So by monitoring the concentration changes in terms of the potential, we will be able to estimate the Fe2 plus present in the solution. Clear? Right. Now the experiment basically contains two steps. Titration 1, wherein you are going to measure the potential change as a function of volume of potassium dichromate added, and then the second titration is basically the first derivative of the first titration. So moving on to what are the requirements for the experiment, you need a potentiometer with the electrodes to measure the potential of the reaction going on, and you need potassium dichromate, which is actually the oxidant, and you need a Fe2 plus sample solution, that is what we are going to estimate. Sulfuric acid, right. The sulfuric acid is added basically to assist the potassium dichromate oxidizing power. So what I have done is I have already pipetted out 10 ml of the Fe2 plus solution and 1 test tube full of sulfuric acid, which is basically to enhance the oxidizing capability of potassium dichromate, and some amount of water, the amount of water added sufficiently to immerse the electrodes inside, right. So moving on into the calibration. So before we do the titration, we will move on to the calibration. So this is the potentiometer, and the first thing is you need to turn on. So there is a knob here which you need to turn it on. So let me turn it on, and there are few choices you can make here. There is a compartment A and compartment B. Depending upon where do you connect, you can actually choose this knob to turn to that side. For example, I am using a compartment B, so I shifted this knob into compartment B. Suppose if you use A, this knob should be towards A. To calibrate the potentiometer, you need to shift this knob from this reading mode to the standard mode. This potentiometer contains an inbuilt standard cell whose potential is 1.018 volt corresponding to 1018 millivolts. So to calibrate, you need to make sure that it gets 1018 millivolts. If not, you need to turn this knob to get 1018. So I am turning it to get 1018. So obtain 1018 millivolts. So this potentiometer is calibrated. Then once you calibrate, shift to the reading mode. Then there are two electrodes which we are going to use. One is the platinum electrode, that is the place where we are going to perform the oxidation or reduction, so redox reaction, and a reference electrode, which is basically the standard calomel electrode. So you are going to measure the potential of the reaction which is occurring at the platinum electrode with respect to the reference electrode. Rings both of them in the distilled water prior to keeping in the sample solution. So, it is done, and then I will keep it in the solution, keep it below the burette which is filled with potassium dichromate to the 0, and then also place the glass rod. So, this glass rod is placed to basically stir the solution. So, now you add the potassium dichromate to the solution at 1 ml interval. So, let me add 1 ml and then stir the solution and allow the potential to stabilize, then record it. Okay. Now, I will add further. So, continue to add 1 ml each and record the reading. So, the addition followed by stirring followed by allowing the potentiometer to stabilize, and recording has to be done in a consistent manner, right. So, I will continue to add and record the reading. So, 1 more ml, continue that. Now, you can see that the potential has jumped from the 400 millivolts into almost 700 millivolts when I added the volume of 9 ml, right. So, I will continue to add, though the potential has jumped already, that is because to get a symmetrical S-shaped curve, so which I will explain little later. So, after that rapid jump I continue to add only 3 to 4 ml and record the reading. So, I will stop here, right. So, whatever the records readings has been taken, we will put it in the tabular column, right. So, when I added at 1 ml each from 0, 1, 2, what you have witnessed actually is that there is a small increase in the EMF. At one particular place there was a rapid increase, that was in my case between 8 to 9 ml. So, I will put here 8 and 9. So, that is the place where there was a rapid increase. After that I continue to record for 3 to 4 more ml to basically get this nice symmetric S-shaped curve. The obvious question comes here, why do we see a small increment in the potential up to this place, afterwards there is a rapid increase and then stabilizes. That you can actually infer from the Nernst equation, the one which we have learned already. You might have learned it in the theory classes. You can see that there is a Fe3 plus by Fe2 plus component, chromium 3 plus by chromium 6 plus, as well as 1 by H plus term. As you perform the redox reaction, the concentration of Fe3 plus slowly increases and Fe2 plus decreases, because of which you see only a small increase in the potential. When there will be one stage wherein the concentration of Fe3 plus will be equal to the Fe2 plus. At that time also the potential increase will be slow. Afterwards Fe3 plus will keep on increasing higher and higher. When all Fe2 plus is completely oxidized into Fe3 plus, this term will go up. Because of that reason, the potential rise will be very high. This is not only associated with Fe2 plus to Fe3 plus, you can witness that from this equation. There is also a reduction of chromium 6 plus to 3 plus, that also plays in the role in the potential measured. So, for that reason we are seeing a rapid increase in the potential at the point of complete oxidation of Fe2 plus into Fe3 plus. Right. Moving on to the second iteration, how do we do it? What we do is that, where do I see the jump? From that place, 1 ml prior to that, 1 ml after that. We will add potassium dichromate in a smaller quantity, say 0.2 ml each, right. The obvious question comes, why do I need to add such a small quantity? If you do add such a small quantities, you will be able to capture the complete oxidation of Fe2 plus in Fe3 plus in a better way. For that reason we go for a addition of a potassium dichromate at a smaller volume. That also we do it only 1 ml prior to the place where we see this jump and 1 ml after that. The reason being, if you continue to add from 0, it will be time consuming process. To reduce the time as well as to get a better result, we record the 0.2 ml addition only 1 ml prior to the place where we see the jump and 1 ml after that. So, once again take 10 ml of ferrous ammonium sulfate, add 1 teaspoon of sulfuric acid, add little bit of water, that should be sufficient enough to immerse both platinum electrode as well as the standard calomel electrode, then perform the titration, right. I have done. So, what I have done is 0 to 7 ml, 1 ml interval, I have recorded the potential, and then between 7 to 10, I have recorded 0.2 ml interval, and it is tabulated, right. Delta EMF is basically the difference between the two consecutive values. Delta V is basically the difference between the two consecutive values of volume of potassium dichromate added. Delta EMF by delta V is basically this divided by this column, and average volume of potassium dichromate is basically the average taken between two consecutive values of volume of potassium dichromate added. Now, if you plot delta EMF divided by delta V as a function of average volume of potassium dichromate given in this tabular column, you would see an increase in the difference in the potential reaches the maximum and falls. It more or less follows a Gaussian pattern. The peak, the volume corresponding to the peak is actually the volume of potassium dichromate required to completely oxidize Fe2 plus into Fe3 plus. That you need to note it down as V1, and the N1 is the strength of the potassium dichromate, which is given to you already. V2 is actually the amount of ferrous ammonium sulfate you have pipetted out for the titration, which is 10 ml. So, if you plug in all these parameters, you will get the strength of ferrous ammonium sulfate, given ferrous ammonium sulfate. To find it out the amount of ferrous Fe2 plus present in the 1 liter of solution, you multiply the strength with equivalent weight, which is 55.85. So, you will get it in the grams. Thank you.